let's start with something that most of the class does bad on. Well, not most of the class. I would say out of all of the questions, like people tend to perform lowest on this. So let's start here. Language transformation. I took this from an old exam. Assume L is regular. Sigma is 0, 1. Assume 0 index 0. The first bit is at position 0. So this is index 0. Prove that the language flip every third character L, where you apply the operation flip third chars W to every string in the language is also regular. So we have a language L. It's an arbitrary regular language. We don't know what the language is, we just know it's regular. We want to prove that if we take all of the strings in L, flip the third character of every string in L, and take that new language, we'll call it L prime, that language is also regular. So to prove that a language is regular, there are multiple options. We build a regex, we build an NFA, or we build a DFA. So to prove, I'm going to call this just F of L, like your grade on the exam. To prove F is regular, we build an NFA for F. But before we do that, let's understand the language. I always recommend just drawing out some examples. So let's draw out some examples. So flip, we want to apply the let's say we have the language L that's just equal to 0, 0, 0, epsilon, 1, 0, 1, 1, 1, 1, 1, 1, 1, 1. Okay. If we apply the operation flip odds L, or flip every third character in L, so every string in this language, the new language that we get, so, we're 0 indexing. 0, 1, okay, yeah. So there is no third character to flip here, so this stays the same. There's no character to flip here, this stays the same. If we're 0 indexing, we get 0, 1, 2, 3, and we flip this. So what do we get? We get 1, 0, 1, 0. And then if we're 0 indexing here, we get 0, 1, 2, 3, so we flip this one. 0, 1. So 1, 1, 1, 0, 1, 1. So we have a language L that's regular. We apply the function flip every third character to every string in the language L, and we get a new language. Yeah?
Don't you flip the 0 to L?
Yeah, I do. Wait, where?
For all the strings. In the example they gave, they flipped the 0 with bit.
They flipped the 0 with bit. Okay, cool, we'll do that. Thanks. So this was 0, this is 1, and then this is 0. Okay. And the last one as well. So we want to build an NFA that accepts this language. So in order to do that, simple diagram I always like to draw. Okay, this is my machine M that accepts L. So this is M, a DFA, that consists of this accepts L. And I want to build an NFA, so this is my DFA, that accepts F of L. So I get an arbitrary input string here. We'll just make up a string. I'm standing here. 0, 1, 1, 0, 1, 0, 1, 0. I take the first character, I flip it, so this becomes a 1, and then I pass it into the machine. I pass the second character indirectly. I pass the third character indirectly. 0, 1, second character. I pass now this third character again. I flip it, and then pass it in. 0, 1, 2, 3. So I pass all of these in normally. I come back to this third character, and then I flip it, and then pass it in. And if the light glows on the end, if the light turns on at the end, then I know the DFA accepts the string. So let's start here. So what are some of the things I need to keep track of? Well, first, I need to keep track of, hey, is the character that I'm passing into the machine something that I should be flipping or not? So, in order to know that whether or not I'm flipping, I can try using true or false. What's the issue with using just true or false? So let's say I make my new set of states, Q prime. So M prime is a tuple that consists of Q prime, S prime, A prime, delta prime, and sigma prime. So I either have two options, I flip or not flip. So I say, hey, I want my Q prime to be Q cross true or false. Why won't this work? Yeah.
You don't track it as like the first one or the second one that you go to.
Exactly. So the reason it doesn't work is because how do I know that I'm at an index mod 3 character, right? Like I need to say, hey, I saw a true, and then I saw a true, and then, or sorry, I saw a true, and then I saw two falses, and then I see another true and flip that, right? So we need to keep track of whether or not to flip. So if we're flipping every third, the process that we're going to follow is flip the 0th index. Don't flip, we'll call this normal. Don't flip the first index. Don't flip the second index. And then we want to flip the third index. Right? So if we were to represent this, we can call this just visually. We can think about this process like this, right? Where we sort of follow the cycle. So with true or false, I have two states, two kinds of modular positions in which I don't switch. So true or false won't suffice. So let's add a third state in order to not flip. So we'll call this flip. Come up with two names that actually mean something, if you can. I can't, yeah.
Like N1 and N2.
Cool, we'll call it N1 and N2. So here we are. So in our start state, we flip the first bit, right? So we start the execution of the DFA, the old machine that we have, the DFA here that we're using as a black box. We start executing from the start state of that DFA, and we know that the first bit that we pass into that DFA is something we want to flip. We know that the set of states in the new NFA, M prime that we're constructing, are tuples, where the first element of the tuple is one state from the old DFA, and the second element in the tuple is flip N1 or N2. So the first element is an old state. The start state was S. The second element is one of these three, and I want to flip the first character, so I'm going to assign it flip. Okay? Now the accepting state, or the set of accepting states. So I just said that I'm not guaranteed that all of the strings that I get in input are going to be a multiple of length of 3. What if the input string that I get is of length 2? If I get in a string of length 2, the only thing that I flip is the first bit, and then I have the second bit, and I just pass that in, and if the DFA on the desk accepts that string, well then, I'm in the language. So, if I have strings of length 0, whether or not I accept is just determined based on whether the DFA accepts epsilon. If I have strings of length 1, that means I flip the first bit, pass it in, and see if the DFA accepts. If I have strings of length 2, I flip the first bit, pass the second bit as is, and see if it accepts. The point is, it doesn't matter whether my flag, when I accept, is in flip, normal 1, or normal 2. Because my strings can vary in length, and as long as I've made sure that I've flipped the right characters, I'm okay. I think. So, do we agree that we can represent this as accept, cross, flip, N1, N2? Does that seem reasonable? Okay, great. So, we're not going to introduce any new characters into our character set, because I don't think we need to. I don't even know if we're allowed to. Maybe we are, I don't know. Now this is the tough part. So I want to reiterate that the states of our NFA are tuples. Q, comma, flag, right? Where this Q is a state of our old DFA. That is formally Q belongs to the set Q, which is the set of states of our old DFA here. And our flag is one of the three that we defined. So let's say I'm in some state, delta prime. My current state is Q, comma, flip. Okay? My NFA is in state Q, comma, flip. That means that the next character that I pass into the machine needs to be flipped. So if I read in a character C, let's say I read in a character 0. What character should I pass into my DFA? 1. So if I am in state Q in my DFA, and I pass in the character 1, what state do I end up in? So I'm in my DFA. I'm in state Q. I pass in the character 1. What is the state? We don't know. Unknown? Sorry? Yeah.
The old transition function Q given the...
Right, exactly. So this is the old transition function, which is the transition function of our DFA, not our NFA, applied to Q after reading character 1. So remember, the first element of the tuple in our NFA is a state of the old DFA. So the first element in the tuple is going to be delta Q after reading 1. And then I transition from flip to normal 1 because I'm updating my mod. And because this is an NFA, I have a set of states. Questions so far? Okay, let's say I was in some state Q, comma, flip in my NFA, and I read a 0 instead. So if I read, I read in a 1 instead, and I need to flip the character. Well, if I'm in my NFA, and I know I read in a 0, or I read in a 1, and I know that the next character, I need to flip it before passing it in, I go to delta of Q, comma, 0. Agreed? So I can either write this out explicitly, or I can just say, this is some character C, and this is some character C complement. So I don't need to write two transitions. And to be formal, I can say that Q belongs to the set of states, capital Q, from my old DFA. And C is a character in the alphabet 0, 1. Now, if I'm in some state now, so going back to this diagram, I flipped the 1 and I've passed it in. Now I'm here. Okay, I read in a 1 as input. This is not a bit I need to flip. So I pass in the 1 directly into the machine, but the only thing that I changed is that I'm transitioning from the normal state 1 to the normal state 2. So I pass it in, delta of Q. I pass in C directly. And internally, I update that I'm now in my second normal state. Okay, now, so I've passed in, I've flipped once. I've passed in normally once. This character, 0, 1, 2, I don't flip this character, right? I'm in my state normal 2. I pass it in directly. But after passing this in, what do I need to do in the next state? I need to flip it again. So I'm in some state Q, comma, N2. I read in character C. In the state M2, I pass in the character directly into the machine without flipping it, but I make a note that the next character that I read, I need to flip. So pass it in directly, Q comma C. And the next character that I read, I need to flip. Q belongs to Q, and C belongs to the character C. Questions? Yeah.
So go up to that little diagram you drew for flip nominal. So this is essentially the same as going through the DFA M and that little diagram in parallel, just making some
Yes,
changes.
that's exactly what it is, right? So the set of states I have originally is Q. And I'm just literally, you can think about it as a parallel execution on the DFA and this. However, it's not quite a parallel execution because if you think strictly about two things that can happen in parallel, they can happen, well, not necessarily, you could say they happen asynchronously, but they can't happen asynchronously because when I'm in this state, I need to flip to it. So kind of, but yes. Does anyone have any other questions about this? So let's say this. Did I need to build an NFA for this problem? Well, I obviously couldn't have made a regular expression. But what if I want, do I need to actually leverage, do I ever use the non-determinism of an NFA in this question anyway? No. So if I wanted, I could actually just get rid of this, and then this, and this, and then this, and then this, and then this. And I missed this. And then I can build a DFA. And both are valid answers. So I built a DFA that accepts the language, therefore it's regular. Or I built an NFA that accepts the language, and therefore it's regular. Questions? Yeah.
This is just like, I'm missing out out here, but
Yeah.
could you like create a regular expression that's representative of like doing the XOR function and then intersect that with this language to like prove that they're both regular?
Okay, so could I create a regular expression by taking, sorry, say that one more time? So you want to leverage XOR somehow.
Yeah, so I want to create a regular expression that's representative of XOR
Mm-hmm.
and then intersect that with this language and like doing so proves that they're both regular or that this language is regular too.
So when you take the intersection of two languages, so the idea was, can I create a regular expression using XOR? So like the regular expression for XOR, A XOR B. If you have two languages, I think it's just A complement B plus, all right, the intersection of the complement of A and B, union, I think this is what XOR is in Boolean logic. But the issue that I'm seeing with this is you want to prove that the language flipped every third character is regular only when L is regular. So if L is a regular language, then the language obtained by applying the flip odds operation on L is regular. If you could express the flip odds operation as a regular expression in terms of L, then you could do it. I'm not sure if I can think of that on the spot. If you can think of a way to flip every third character as a regular expression in terms of L, and claim that when I apply that regular expression to L, the language that I obtain is flip every third character of L, then yes, you could argue that.
Wouldn't that be something like 0 or 1, 0 or 1, 0 or 1 star?
Yeah.
0 or 1. Sorry, say that again?
Maybe like 1 0 0 star because you want to start.
Yeah, exactly.
Yeah.
I'm not sure. I'll have to think about it. Interesting idea, though. Okay, do you guys want to do another example of language transformation? Do you want to move on to PDAs, pooling sets? Should I go through another one? It's up to you guys. Yeah.
So I feel like there's like similar examples to that one where it's like you flip every like third or every even or every odd or whatever.
Yeah.
But could they have a question where like the condition is different, where it's maybe like flip after you've read a string like 0, 1, 1 or something like that?
Flip after you've read a string 0, 1, 1.
And like how would you do that?
Let's think about that. Well, let's say I wanted to ask flip after you've read a string 0, 1, 1. And do you want to flip after the first occurrence of reading 0, 1, 1? Or do you want to flip after every occurrence of reading 0, 1, 1?
Either one, I don't know. I mean,
Okay.
let's maybe just do first occurrence.
All right, let's think about this. So I've seen 0, 1, 1 is a substring or a subsequence?
Substring.
Okay, so subsequence would be easy, right? Because what you could do is you could have a flag saying scene 0, scene the first one, scene the second one. However, you would almost need to build a DFA with flags. You would build a separate DFA to think about. You can build a DFA easily to accept strings that have 0, 1, 1 as a substring, right? If you think about the idea that he said, this is essentially a parallel execution of Q and this DFA that I've written here.
Oh yeah.
So you replace this DFA with one that represents the language scene 0, 1, 1 as a substring,
Yeah.
and it may be possible. I don't want to say it's definitely possible, but I think you can construct a DFA with flags. Yeah.
Isn't the whole point if you construct a DFA with flags, like in that sense that it's not able to be represented as a regular language? Like wouldn't that in essence prove that it's not regular?
No. So if I can build an NFA that accepts, or if I can build a new DFA that accepts the language that I obtain after applying the transformation to the string, my new language is regular. This, you could think about this as a DFA or an NFA, right?
Mm-hmm.
So I would say the answer to that question is no. So yeah, sorry. What do you guys want to do? Do you want to do another example of a language transformation with a different condition, or do you want to move on to PDAs? Move on. Okay. So let's see if I can. Does anyone have a question in mind for PDAs? Okay, let's see if we can. Let's design a PDA to accept properly nested parentheses.
Leak code problem.
Yeah, it is a leak code problem, sure. So how would you solve this problem using leak code? Like what data structure would you use? A stack. And what does a PDA have?
A stack.
A stack. So naturally it follows that you should be able to do this, hopefully. So like this is in the language, right? So my character set is now this set of open parentheses and closed parentheses. This is in the language 1, 2, 3. Oh, this is hurting my brain. This is in the language, right? So does anyone think we can design a PDA to do this? How would you go about designing a PDA to do this? If you can design a PDA to do this. Well, what do you do? Yeah.
So you could have like two states.
Okay. So two states. Let's label them Q0 and Q1.
Yeah. And Q0 is accepting.
Okay, so this is my accepting state. Okay.
So if you read an open parentheses
Mm-hmm.
from Q0, you push it onto the stack
Okay.
and then go to Q1.
Okay, so if you read an open parenthesis from Q0, push it onto the stack and then go to Q1. So recall that, just for clarity, this is the character that you read from the input string. This is the character that you push or pop in the transition function. Pop. And this is the character you push. So you're saying if I see a parenthesis, push it onto the stack. So I read an open parenthesis from the string. I pop nothing off of the stack. And I push the open parenthesis onto the stack. Okay.
Yeah.
Then?
Or actually, maybe you need three states. I can just. say what I was thinking originally.
Sure, sure. I mean, we'll try it, right? It's an iterative
Yeah.
process.
So then for Q1, you put a state back to Q0 where you have to
So let's say we read, we can try putting a string on the stack, right? So we read some like open parenthesis.
yeah. So then, if you read a close parenthesis,
Mm-hmm.
you have to also like pop an open from the stack.
Right, so if I read a close parenthesis, we want to pop an open one from the stack.
Yeah.
So if I read a close parenthesis, I pop an open parenthesis off the stack and push nothing onto the stack.
Yeah.
Okay. Does this work for all cases? Let's see. So what if I read two open parentheses in a row?
Yeah, that's the issue.
Yeah.
Don't you have to use like the dollar sign thing?
We do need to use the dollar sign thing at the beginning or the end, so we can add that on if you want. You read nothing, you push nothing onto the stack, and then you push a dollar sign onto the stack, right? But I think that comes later at the end. Anyone have any other ideas? So we know how to solve this in LeetCode, right? You keep pushing, push open parentheses onto the stack. Yeah.
Isn't it a self loop to Q0 with open parentheses and then there should be an epsilon transition to Q1?
So you want a self loop on Q0.
Yeah.
That does what?
This the same thing as the transition from.
Okay.
Basically just move that transition to the self loop.
So erase it here.
Yeah.
Okay. So move this transition to the self loop. And should I erase this as an accepting state? Yeah. Okay. Great. So I've moved this transition over. Then what do we want to do? So now we're pushing all of the open parentheses onto the stack. Then what?
Epsilon transition to Q1?
Epsilon transition to Q1. So you want to read nothing, push nothing, pop nothing?
Yeah.
Okay. Then what do we want to do?
That Q1 transition should probably be a self transition as well.
The Q1 transition should probably be a self transition. Did you want this arrow to go up or down? Or both ways?
Both ways.
Okay, so we'll add it. We'll just say, okay, yeah. And then what did you want?
Self loop on Q1 but with closed parentheses.
Self loop on Q1 but with closed parentheses. So I read a closed parentheses from the string. I pop an open parentheses off of the stack and then push nothing onto the stack, right? Okay. And then do you want to finish the dollar sign thing? Or are there any other transitions you want to add? So what do? We read nothing from the input string, we pop the dollar sign off the stack, we push nothing on. And then let's see if this is an accepting state. Let's try it with a few strings and let's see if it works. So let's take this string as an example. So we push our dollar sign onto the stack. We read an open parenthesis, we pop nothing, and we push the open parenthesis onto the stack. Okay. Then we epsilon transition, oh no, we read another open parenthesis and push it onto the stack. We epsilon transition down here. So there is no other open parenthesis even if we wanted to read this, right? So we have to take this transition down here. We read a closed parenthesis, we pop an open parenthesis off of the stack, and we push nothing onto the stack. Now what do we have? We have an open parenthesis, right? So even if we wanted, we can't use this transition. We have to take this epsilon transition that we did and go back up. We read an open parenthesis from the input string, pop nothing off of the stack, and push it onto the stack. Okay. Now there's a closed parenthesis, so again, I can't use this transition here. I need to go back down. So I consume a closed parenthesis from the input string. I Did I screw up?
No, I think it's fine.
Oh yeah, I consume this. I pop an open parenthesis off the stack, push nothing. Then what do? Same thing, same transition. I sort of lost track of what I was doing when I got the notification. Same thing. I pop the $sign off of the stack and then I end up in an accepting state. Yeah.
There's an issue with this.
There's an issue. What's the string that doesn't work?
Like open, close, open. This PDA would accept it. Right?
This PDA would accept it.
Yeah. No?
Let's see. So let me delete all of these other transitions. So what is it? We push open, we read open, we pop nothing off, and we push. So we have our $sign, we push open onto the stack, right? We move down, and then we pop, we read the close parentheses, we pop the open off of the stack, and then we epsilon transition. Then we go back up, we read an input string, C, right? We pop nothing off of the stack, push the open parenthesis onto the stack. And then we come back down here, and then I don't think we can do anything.
Yeah, but that's because it's an NFA. Like at any given point, you take all possible paths, right? So after you read the second character, the close parenthesis, you're in Q1 and your stack is empty, so you can just go to accepting, right?
You're in Q1 and your stack is empty, so you can just go to accepting. Is it empty?
Well, there's just the $sign, right?
Right. Can you see this? Say the string again. What was it? Sure. I'll just
open, close, open.
Open, close, open.
Because you don't have to read the whole string, right?
You do need to read the whole string. You need to read the whole string. We had this discussion last time. You need to read the whole string. Your stack needs to be empty, and if one of the possible paths leads to an accepting state, then you're in an accepting state. Well, the way we designed it with the $sign, it does, right? In this case, because we put the $sign.
Wait, so
what was the string? It was open, close, open. Yeah. Okay. So let's trace through it. We push the $sign onto the stack. We read an open parenthesis from the input string and push it onto the stack.
Yeah.
We epsilon transition into this state.
Yeah.
We read a close parenthesis, we pop an open parenthesis off of the stack and
so
push.
at that point, you're in Q1 and you only have the $sign, so you can just arbitrarily take it.
Yeah, but if I take this $sign and pop it off the stack, I still have not consumed the entire input string.
Oh yeah, so when you read the last one,
when I read the last character, what do? There's no transition function, right?
Yeah, so
then you like pull a crowd strike and blue screen of death.
Okay, that makes sense.
Yeah.
So you do go to the acceptance state, you just end up leaving it.
And there's an undefined transition. So you can think about it as like falling off the face of the earth.
Okay. That makes sense. Thank you.
Wait, questions? Should we move on to fooling sets? Yeah? Okay.
Can't you collapse Q0 and Q1 into the same state?
Can I collapse Q0 and Q1 into the same state? Probably, because there's an epsilon transition between them. Okay.
Wait.
Yeah.
Could you write the CFG for this? Because that was the making a PDA into the
Okay, let's see if we can write a CFG for this. It may be tricky, but let's see. How do we write a CFG for this? Yeah, exactly. Oh god.
Well, because I had this question on like something, and I was so confused.
Yeah, I'm thinking. How do you write it? Let's think about why you would need to write a CFG for this first of all. If you have a question that says, let's go through this. If a question says prove that the following language is context free, then building a context free or push down automata suffices as a proof to show that it's context free, right? If something says prove that this language is regular, building a DFA, NFA, or a regex proves that it's regular. So the only case in which you would need to do this process of conversion from a PDA into an actual set of production rules is if we specifically ask you to.
I think the reason we had this question was because one of the questions specifically asked you to.
Oh, when? Or in like a previous lab?
Or like
Yeah. So let's see. The set of all open and closed parentheses. Can anyone think of a good set of transition rules? This seems kind of tricky actually. So the thing is when you open a if you have a set, let's use the recursive approach. So someone else gave you a string that has a proper set of open and closed parentheses, right? So W is an arbitrary string that has a proper set of open and close parentheses. So what can we add on to keep this properly nested? Well, there's three options. If this is my x, I can add this on, right? If I take this, I can add this on, or I can add this on, right? Is this the set of production rules? Like, if I say S leads to epsilon, does this give me the set of properly nested parentheses? Yeah? So the approach I use is, suppose, as I said, like with recursion, suppose someone else already gave you a string that's in the language. What's the smallest thing that I can add on to keep the string in the language? That's how I like to think of it. So to answer his question, how do we make a CFG for this? We have a start state that goes to epsilon, or I add properly nested parentheses to the left, or I add properly nested parentheses to the right. Or I do this, and then you can argue that you may not need the left or right thing. You may not need both of these. Possibly. I haven't thought it through. But keeping both of them there won't make it wrong. Okay, fooling sets. So, so the concept, and who asked about fooling sets? Okay, the concept first of all, and then examples, right? Okay, great. So the concept is, so in order to prove a language is regular, we make regexes, DFAs, NFAs. The word DFA, NFA, deterministic finite automata, non-deterministic finite automata, has the word finite in it, which means we need a finite number of states. So can we decide if a given string is in the language with a machine that has a finite number of states? The argument of fooling sets is that we would need an infinite number of states in order to decide if strings are in this language or not in this language. Thus, an automata that's finite cannot decide this language, thus the language is irregular. So conceptually, does that make sense? Yeah. It's a very high-level overview. There's like a mathematical proof of countable and uncountable infinity, which, to be honest, I really didn't understand when I took the class. So, let's look at examples. Wait, I think someone had a question. Did you have a question?
Yeah, I was going to say real quick, can't they be simplified at CFG? Because
Probably, yeah, you don't need both of these, right?
Yeah. I think you just do SS.
Yeah. So examples. Do you guys do any of this? Let's hope nothing naughty is open. Okay.
Oh yeah.
This is the archive. Let's look at your homework. CFGs. Let's take this problem. So we have, I remember someone asking about this in office hours. You have language 3b, 1 to the power of k, such that y belongs to 0, 1 star, and y contains at most k1s for k is greater than or equal to 1, right? And then this said y contains at least k1s for k is greater than or equal to 1. Let's take the case that y contains exactly k1s. Okay, so I'm taking the subset of the language that's common to both of them. So let me put it this way. So intuitively you may stop and say, wait a minute, he's taking a subset. One of these languages is regular and one is irregular, if I remember correctly from the homework. He's taking a subset of a regular language, and he's taking a subset of an irregular language. So would that, if he's already taking a subset of an irregular language, wouldn't it be irregular? So you could think about this. So this naturally leads to two questions. Is every subset of a regular language regular? No. Counterexample.
They gave one of Piazza as like technically 0 to the power of 2 to the power of n is a subset of 0 star.
Yes, and that's irregular, right? Another thing you could say is 0 to the n, 1 to the n is a subset of 0 star, 1 star, right? Okay, let's look at it the other way. Is every subset of an irregular language irregular? Well, this is trivially no, right? Because one subset is the empty set. So trivially, the answer is no. So anyways, that's why this question is non-trivial. Let's see if it's regular or irregular. So the language is L equals 1 to the power of k y such that y has exactly k ones. So intuitively when I look at this, it's like, how would I know how many ones there are unless I counted the number of k's? And if this language is infinite, then I could have as many k's as I wanted. And I don't think I'd be able to decide this in a finite number of states. Does anyone think this language is regular? Does anyone think it's irregular? Does anyone not know? Okay, cool. Does anyone actually want to raise their hand?
Wait.
Oh, what's up? Did someone say wait?
No, no.
Oh, okay. So this will also hit on language classification number 4, right? Is this language regular or irregular? If it's regular, give me a DFA, NFA, or regular expression that captures the language. Can you try to construct one?
No.
How would I try to build a regular expression for this? Yeah.
If y has to have exactly k ones, then it's an even number of ones.
If y has to have exactly k ones, there needs to be an even number of ones in the string. Yes, I think so. Right?
But yeah, so in this, at least two states when C one number is one.
Yeah. So let's take a look at the bound that they put on k, the lower bound that they put on k. So they said k is greater than or equal to 1. So what he cleverly pointed out was, if I have k1s here, and I have k1s here, then the total number of ones that I have is 2k. However, I need to guarantee that exactly k of those ones are at a prefix. So you said it's not as simple as just saying any string with 2k ones, right? An even number of ones, and you have 2 states and flip, because k of them need to be at the prefix. So what if we used an NFA, and then idea. What if we used an NFA, right, with 1, and then we epsilon transition, and then we use another NFA with 1s here, right? So we guess the first k ones. Well, what's the issue with that? We could end up accepting strings, because of the epsilon transition, we could end up accepting strings that are actually not in the language, right? So 1s need to be at the prefix. So I'm struggling to come up with a regular expression, or an NFA or a DFA that can decide this. So I'm going to guess that the language is irregular. This is the process you need to go through. There's no algorithm that'll tell you this is exactly regular or irregular. You just need to try. So let's say we guess it's irregular. What could a fooling set be? Sorry? 1 to the power of k. Or we could even just say 1 star, right? So what is one prefix? 1 to the power of a. Another prefix is 1 to the power of b. What's a suffix that puts one of these strings into the language? 1 to the a. Puts this into the language L. And if I put 1 to the a here, this is not in the language L. Let me think about that. Assume, well, A and B by definition are not the same, right? So I was thinking, wait, could I restructure? So the claim is that A, first of all, A is not equal to B. However, if the sum of A and B is even, so if sum of A and B is even, right? Let's say A is equal to 2 and B is equal to 4. Then I could rewrite this as 1 to the 3, 1 to the 3, and it would be in the language, right? So what if I strictly fix that B is equal to A plus 1? Now I have an odd, now this sum will be odd, and I won't be able to split it, right? So I think this language is irregular. You still seem confused? Yeah.
Can you explain that? Like,
Okay. So I said we're trying to decide, we're not sure if this language is regular or irregular. We started by trying to build a DFA or NFA. He cleverly pointed out that if it's 1 to the k, y, and y has exactly k ones, then the total number of ones in the string is 2k, correct? Which means this is pretty much strings with even number of ones. However, the caveat is that exactly k of those ones need to be a prefix to the string, which means that I can take any string with 2k ones k of the ones, let's say k equals 3, need to be a prefix. So it's not all strings with even number of ones. It's all strings that have an even number of ones such that that even number is equal to 2k, where exactly k of the ones are at a prefix. Correct? Good so far? So the approach was, what if I tried building an NFA to accept this language? Maybe it's regular. So I try to build an NFA. I get an epsilon transition, let's say here. And I guess that I've read k ones. Let's say I make a guess. And then, what do? I put 0, 1 here. I absorb the rest of the ones and see that I've accepted. So I'm just trying to build an NFA that accepts this, right? So does this, let's start here. Does this NFA accept this string? Does this NFA accept this string? Yes, right? So it takes 3 ones, epsilon, and then it reads everything else, right? Question, does the NFA accept this string?
Yes.
But k is not the same, right? So this is not going to work. So I'm struggling to build an NFA or a DFA that accepts the string. I'm not able to. That's making me think that the language might not be regular. Good so far?
But doesn't it say that y has to have?
Exactly. So y has to have exactly k ones. Y needed to have 3 ones, right? But this NFA that I built accepted it when it was 4 and 3. So what this is saying is I'm having a hard time building an NFA that accepts this language, right? I'm struggling. I'm not able to do it. This is making me think that because I can't build a finite automata that accepts this language, the language might be irregular. Good so far? So, okay, now I think it's irregular. How do I prove that it's irregular? I use fooling sets. So what's a possible fooling set? A fooling set that we used is 1 star. Or you can think about it as we pick some n, right? So I take the prefix 1 to the power of a. I take the prefix 1 to the power of b. If I put 1 to the power of a is not equal to b. Good? If I put this, and I put 1 to the power of a, is this in the language or no? Is this string in the language of the question? Is 1 to the power of a 1 to the power of a? Does it follow the format 1 to the power of k, y, such that y has exactly k ones? Yes. Okay, what if I put 1 to the power of a here? Does it follow that format?
Well, it's not the prefix.
Right, so he says no because it's not the prefix, right? The prefix and suffix don't match. Right? So the prefix has b ones, the suffix has a ones. And the prefix had b, the suffix had a, so it doesn't match. But what if, let's take an example, what if b, so we know that b is not equal to a. What if b was equal to 4 and a was equal to 2?
Then you could split it up into 3 and 3.
Then I could split it up into 3 and 3, right? So I get 1 to the power of 4 and 1 to the power of 2. Good so far? This is 6. this is equivalent to the string 1 to the power of 3, 1 to the power of 3, right? And this now has k equal to 3 here in the prefix, and k equal to 3 here in the suffix. So this string could be in the language, right? So what's a constraint that I can put on B in order to ensure that this string never ends up in the language?
B is odd?
B is odd. Sorry, is that what you said?
Yeah.
B is odd, right? Okay, you could do that. Or you could simply just set B equal to A plus 1.
And you can do that without loss of generality, right? Can you do that? Because
Maybe. I'm thinking through this, I just came up with a problem.
okay.
So if B is equal to A plus 1, the sum of B and A will be odd, right? And then if the sum is odd, you'll never be able to split it into equal partitions where you have two K1s. Does that make sense?
And because that is a possibility, it's not.
Right, that's why it's not regular. Yeah. Okay, like 4 hands are right.
Could we just look at the subset of y's that start with 0 and use that?
Could we look at the
Yeah.
subset of y's that start with 0 and use that?
That's what I did.
Well, what's the subset of y? Oh, the subset of y's that start with 0. Okay, so he wants
Because I
to...
think those enough would be alone to prove that.
Okay, sure, let's try this. So you want to keep the fooling set the same. So this was approach 1, right? Let's look at approach 2. So you want to say we take 1 to the A, 1 to the B. What do you want to use as a suffix?
0, 1 to the a. Yeah.
Yeah, and then 0, 1 to the A, right? So now the string is never splittable, correct? And no matter, so A is not equal to B, the string can no longer be split down the middle like it was here, right? There's no way of putting that string into the language if A is equal to B. So if you use this suffix, the first string always ends up in the language, and the second string never ends up in the language. Simpler example. Does this make sense? This is kind of the thought process you have to go through in these questions where they ask you to classify whether a language is regular or irregular. It's not like you can just look at it and tell, oh yeah, this is like, sometimes you can, but it's not a like fixed science. Yeah.
So why isn't the second string in the language?
Because the prefix of the string is 1 to the power of k, right? So k is equal to b. And y, at the end here, needs to have exactly k1s. So this y has a1s, not k1s, right? So it's not in the language. How are we doing on time? We're over. I'll do one quick example, but if you need to leave, go. So let's take the language. Is this language regular or irregular?
Irregular.
Irregular. Okay, let's see.
There
So
was a similar example of this somewhere.
in the summer.
There was a similar example of this somewhere.
Okay, so let's condense these two into one for now, right? And then we'll take 1 to the n, and then we'll take sigma star, and then we'll take 0 to the n, such that n is greater than or equal to 1. Okay, now what? If n is greater than or equal to 1, actually this might be regular. Here's why. N needs to be bigger than or equal to 1, right? So I need at least one n here. Well, no, let me think. And then the rest of the string can be absorbed into here and here. So if I put 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, right? I just need to fix one of these 1s to be 1, fix one of these 0s to be 0, and fix this 0 to be 0. And this can be what? Sigma. This can come from sigma star, and then this can also come from sigma star, right? One person's nodding, right? So this language is actually regular. Because if n is bigger than or equal to 1, what's the regular expression for this language? What is it?
0 sigma star 1 sigma star 0 sigma.
Yeah, so it's regular. Because there is a way of consuming and splitting the strings. Okay, hands, yeah.
My question, like with these things, is how does it scale? Right? Like it's regular for one. You can say if n equals 2, it's also regular, but across the entire thing.
Well, how does it scale? N can be bigger than or equal to 1, right?
So if like,
So as long as I have 1 here, no matter if I put n equals 2, 3, 4, 6, 3 million, right? You can absorb that into sigma star. So if n was 2, right? I don't care. N is 1 and this is sigma star.
okay, so when then 0 to the n or 1 to the n, why is that irregular? When n is greater than or equal to 1?
Because, so you're asking why is 0 to the n, 1 to the n, the language irregular? In comparison to this, right. Because
two, right?
the reasons 0 to the n, 1 to the n is irregular is because there's no way of distinguishing 0 to the power of 3, 1 to the power of 4, versus 0 to the power of 3, 1 to the power of 3 with the DFA. Here, I have multiple ways of parsing and splitting the strings such that they're in the language. So if I take the string, let's take a different example, okay? Let's say we take the string 0 squared, we'll put some 1, 1, 1 here. We'll put 1 squared. We'll put 0, 0, 0. And we'll put 0 squared, right? So your example is with, how does this generalize, right? Now we have n equals 2. Well, actually, the string is just 0 dot 0, 1, 1, 1, which is this part, right?
Yeah.
1 dot 1, 0, 0, 0, which is this part.
You
And then-
disappeared.
It came down.
Oh. Yeah, okay, which is this part. And then I take the 0 and I split it. I take 1, 0 from here and I add it here, right? So now this can just be my sigma star.
Sure.
This can be my sigma star. This can be 1, this can be 0, this can be 0. So this language is regular. Because even if it's not the same, or even if n is bigger than 1, I can absorb the string into the sigma star. And at least one way of splitting it will put it into the language. I'm out of time, so I'm going to end. 1 second.